Hello, I want to talk a little bit about cosmology and the shell theorem. The universe is isotropic and homogeneous. That's called the cosmological principle. That means if I look out at the universe from this point of view, I could envision that the universe is composed of uniform density shells. These are concentric shells, and they continue out for infinity, away from me, the observer. On the other hand, if I have an object out here, it also has the experience of seeing the universe as composed of uniform density shells, concentric shells, going out for infinity. So what is your immediate reaction to this? If I asked, what is the force on this particle? And what is the force on this particle? Obviously, since everybody sees an equivalent bunch of symmetric concentric shells, the force on each observer in this system is going to be 0. I would say that was obviously, except that a large number of really well-trained cosmologists disagree with this. Okay, they disagree with this. I think I can actually prove it. We can integrate, but instead of integrating with the shells, which could lead to some kind of possible error involving partial sums, I'm going to use concentric cylinders. But first, let me talk about what could be an error involving partial sums. Partial sum. The partial sum in question here is a partial sum of the variety infinite sum as n equals negative infinity to infinity of negative 1 to the nth. And it looks a little something like this. Negative 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1. And each of these minus 1s and plus 1s cancel out, so that given any point on the system, you've got a 0 net force because you've got an equal amount of matter pulling either direction. Now, I would like to kind of argue that the sum of negative 1 to the nth is basically 0. There is argument about that in some places. That I've read arguments that if we call this S they define it S equals negative 1 to the nth of n equals 0 to infinity. And they actually end up saying that 1 minus S equals S, and then solving that to get 1 equals 2S, and they come up with S equals 1/2, which is, well, you're working with infinities. But my point is going to be a different nature, that when you sum up together negative 1, this sum can be anything you want. Anything you want. And how is that done? Well, let's say you ask this guy how much force is on the rope. What he's going to do is he's going to say, I see me and 4 other guys in front of me pulling on that dot over there. So that's minus 5 men's force, or probably about 500 pounds pulling to the left. And then he's going to say that this guy and this guy are going to cancel out, and this guy and this guy are going to cancel out, and that guy are going to cancel out. And so we can get an answer of a force of 500 pounds to the left on that guy right there. And similarly, if you ask this guy, he's going to see himself and these 2 other guys contributing 300 pounds to the right on that object. So he'll say, and then everybody else forward and backward is going to cancel their forces around him. So he'll say there's 300 pounds to the right on that object. Now, of course, in the situation that I've drawn here, you're going to have basically an infinite tension in the rope, probably everywhere, and somewhere the rope is going to break, if not on a fairly regular basis. But if you sum up the forces on this point, does it really make sense to just pick an arbitrary for each person to just decide, I'm going to count the people between myself and the people between me and that point? Or would it make more sense for them to try to imagine the situation from the perspective of that point to calculate the forces? So I'm going to kind of invoke a principle of force feeling. I'm not sure if I have a proof for this, but I think that in order to calculate the force felt by an object, you must do it from the perspective of that object. In other words, don't use a method that leads to asymmetric partial sums. Or more rationally, if you use this, you only need to do this. Let me erase that. You only need to do this if you're using a method that leads to asymmetric partial sums. So now I want to show how Newton's shell theorem leads to asymmetric partial sums of an infinite series. Here's the basic idea. We have an observer right here, and then we have the point around which we want to calculate the force over here. And so what we're going to do is imagine the shells around the observer. Shell here, shell here, shell here. And I'll keep drawing shells out until I get out to there. And basically, we say, this guy says, all of these shells contribute a force to the left. Now, after that, you can do integrals to show that, that all those contribute to the left. But then, after that, the next shell around it, I drew this too big to get it all on the map, but I'll just kind of draw it like that. Well, there is this mass of the shell pulls to the right, but the mass over here pulls to the left. And it just happens that the symmetry of this is interesting, and it involves an integral. If I make the big radius r and this radius little r, and from here, little r and r, it involves an integral from, well, we'll call this L, and it involves an integral of L going from capital R minus R to, let's call this square root of r squared to square root of r squared plus little r squared. And then we start over here, and this exactly cancels out with the integral from L equals square root of r squared plus little r squared to r plus r. And so I don't know exactly how to write that, but anyway, the force to the right ends up canceling exactly with the force to the left, and that happens with all of those spheres. So by doing it this way, we basically get minus 1 plus minus 1 plus minus 1. So a bunch of forces contributing to the left, and then you start getting those cancelings. Let me just make sure that that was a dash, not a minus sign. And that was a dash, not a minus sign. Anyway, So obviously Newton's shell method leads to this problem of asymmetric partial sums, but we can do the integral using another geometry, such as an infinite series of concentric cylinders. Here, I envision a situation where the mass m is separated from the observer by a radius r. I also envision an infinitely long cylinder with density sigma aligned with its center along the axis between the observer and the mass. The whole mass of the cylinder is chopped up into tiny differential masses called dm. Each differential mass creates a differential gravitational field at the central mass according to the universal gravitational constant g times the differential mass divided by the square of the distance between the point mass and the differential mass. So I'll call that L, the distance from M to differential mass. The differential mass of the system is going to be equal to the density of the cylinder, the area density of the cylinder, times a differential area element around the cylinder. Now we can use a symmetry argument to say that all of the x and y components on this mass are going to cancel out. So all we're left with is a force in the z direction. So I'm going to say dg sub z df sub z over m, and I'll put a note there, dot dot dot. And what I'm going to do to get that f sub z component is multiply that total force from dm by sine of theta here, which is the angle, which is the length or the proportion of the component of this triangle in the direction of z. So I'll just copy those z's down and the sine theta down. Now we can talk about a differential area that is going from, say, here. Well, I should put it up above. We'll start here where I've labeled the dm, but instead of the dm being just a tiny mass at that tiny point, I'm going to have the differential mass go all the way around the thing, since we've already invoked this symmetry, and that dm, that dA equals sigma dA, that sigma, well, it's just going to stay there. The dA is going to be 2 pi r, which is the circumference of the circle, times dz, which is the tiny differential distance along that cylinder. Now we can replace that sine of theta with the opposite, z minus r, divided by the hypotenuse, L, and we will have an integral we can work with. Pull all of the constants out. The universal gravitational constant is a constant, and the radius in this situation is the radius of this cylinder. It's a constant throughout this context. Sigma is the density of that cylinder, which will be a constant. And we will apply an integral, which goes z minus r dz over square root of z minus r squared plus r squared. And that integral comes out to be 0. And notice that I've got rid of the problem that comes from using the sphere method, the Newton shell method. There was a problem with partial sums before, but now we're taking care of that partial sum. There's no partial sum left because we're going all the way from negative infinity to infinity here. And then we'll notice that since this infinite cylinder contributes nothing to the force on this mass, we can see that none of the cylinders, because we're going to make an infinite number of concentric cylinders around here to do the calculation, and we will find that it always comes out to be 0, and so the total sum is going to be 0. And you can see that since this force is 0, it has no dependence on what the mass is or who the observer is looking. It's always going to be 0. There's no force on that mass due to all of those infinite or due to all of those uniform density shells. It always comes out to be 0. But if you prefer to do it with partial sums, instead of drawing those cylinders, you'll draw spheres around this mass, and you will find that these spheres will, done this way, all of these spheres will contribute a certain amount of force on that mass, and then you keep going outward, and none of these spheres, for this next sphere, the amount of mass in that one exactly cancels out with the amount of mass in this direction. So that one would be 0. So you would get a net total of a force in that direction. So if you agree with my principle of force feeling, that in order to calculate the force felt by an object, you should do it from the perspective of that object if you're using any method that leads to asymmetric partial sums around the distant mass. But if you think that you should do that, then you should have a look at Relativity, Gravitation, and World Structure by Edward Arthur Milne, because most people criticize Edward Arthur Milne's model because they say that it describes an empty universe. That's not what Milne's model does. It describes a model where all of the forces cancel out. So, and you get 0, like this. Now, this whole argument is described on the essence that the amount of material in the universe is actually infinite, and that's the way Arthur Milne kind of described it too. He said that the amount of mass in the universe is infinite. If we assumed that the universe was not infinite, then there actually would be a center of mass of the universe, and you could distinctly say one of these guys is getting the correct result because the matter in the universe is symmetric around him, and this guy might be wrong because he's counting the matter in the universe over here that doesn't exist, or vice versa. So if the amount of matter in the universe is finite, then the equations of modern cosmology actually become fairly reasonable, except that you got to choose the correct center. So last week when I was writing this article about hypothesis versus impression, I said that my current impression of the standard model was that the universe was a finite uniform density sphere out to a certain radius and empty beyond that radius. The reason that I assumed that was because the math works out if you do assume that. But if you assume that the actual radius is infinite and it is not empty beyond that radius, then all you're doing is creating this artificial symmetry, and all of these different artificial asymmetries, wherever there's an incomplete partial sum of an infinite series.